Hello everyone. Here's a little example of how you can have a image of yourself while you're giving a presentation, and we'll do that through some math stuff. We've been exploring the idea that an angle measure can be drawn through a circle, and that angle measure corresponds to the central angle of a circle, but also an angle in a triangle. And because the ratios of triangle sides are fixed, we've given them names like sine, cosine, and tangent to sort of denote that these ratios between side measurements are fixed for a given angle. I simply cannot draw any other triangle dimensions without this being true. So we've been seeing how these functions take an input, which would be the angle created at the center of the circle, and those correspond to outputs being ratios of sides of triangles. Now, we've explored that inside the unit circle, but also how it would map out as a function. And we can see here, as I rotate around through the inside of the circle, if I record the angle measure and the opposite side of the triangle that's formed, in other words, the y coordinate of that point going around the unit circle, it traces out this periodic curve. And this curve represents the sine function. On the x-axis, the input values, which are the amount of rotation around the circle, in radians in this case. And the output on the purple line is the length of that opposite side of the triangle as it grows and shrinks as we rotate around the circle. So this is a really nice way to kind of visualize what's happening and how that curve gets created and how the function sort of develops as we rotate around a unit circle. So this is fun to play with, and I recommend that you do it a lot until you internalize all of these concepts. So let's take a look at a little bit more here. Here's just a flat Desmos graph, and Desmos is perfectly happy to plot the points of the sine curve. And here, an important distinction to make is that currently this function, which is taking an input x, and just to be more rigorous here, we'll call this function f, which takes an input x and gives us an output along the y-axis. For every given input here, though, we have to tell it what kind of units we're measuring in. So if I go to the wrench in the upper right, at the bottom here, there are inputs for radians or degrees. You always have to tell in a graphing calculator what types of input you're giving to the function. So along the x-axis right now, it's assuming that we're rotating in radians. So we can see that we complete half a cycle at pi radians. That's halfway around the circle. And finally, 2 pi around the circle, we've completed all of the outputs of the function. If I switch this to degrees, you'll notice that this thing gets stretched out rather disgustingly across the x-axis. This no longer looks anything like our sine function, but it's simply because now it's showing me the outputs of the function as I input degrees. So this is no longer 4 radians or 4 radius measures around the outside of the circle. This is simply 4 degrees of rotation, which hopefully you can see or imagine is a very small angle indeed. So the length of the opposite side of the triangle, let's take a look at it actually. You can imagine the opposite side of a triangle at 4 degrees of rotation would be a very tiny opposite side. So just the length from the x-axis up to this point, approximately 0.07, which is what was being spit out of the function here when we're in degree mode. Now I can simply change my axes, so I could change the x-axis to, instead of going from -6 to 13, to go from 0 to 360. And now I can see that, there's my nice periodic sine wave It just simply takes longer to complete its cycle depending on the units that we denote are being used for the x-axis or the inputs to this particular function. So be careful of that anytime you're working with these things. So we can switch back to radian inputs, and you'll want to sort of go back and forth between these things depending on the context. When in doubt, if you're not sure what to use, always go with radian measure. It's the safer of the two units. So here's our function, and I always want you to be imagining rotating around the unit circle as you sort of see this periodic wave map out. But at the same time, we need to be able to deal with this as the inputs and outputs of an angle measure and a ratio of sides of triangles. And once we have this as a function, we can manipulate it in the same ways that we've manipulated other functions. So the sine function can be scaled. I can simply take every input to this function and multiply it by a particular value, and every single one of those values gets a multiplier of 2. And I can see that kind of stretching factor or scaling factor occur as I alter that value. There's a special name for this. It's called amplitude, which we will go into more detail later. I can also set this up as a variable slider, and now begin to see this sort of effects of changing the amplitude of this function, the scaling factor. And in fact, this is exactly what happens when you turn up the volume. We sort of mentioned how sine waves describe the vibrations of molecules that cause the pressure in our ears that allows us to hear. And if we turn up that amplitude, that causes a louder volume. So it's another interesting correlation there between these things. In addition to modifying the amplitude of a function, I can do all other sorts of other things inside here. Another really exciting thing we can change is the multiplier of the input. So if before we put the input into the sine function, we multiply it by 2, what happens is I increase the frequency, we call it, of this function. In other words, how many times we see a complete cycle in the same window. So we're going over this in very loose terminology at the moment, but we will formalize this more once we get a sense for how these things behave. So I'm going to give this also a slider so we can play around with it some more. And now when I adjust B, which multiplies the angle measure before it goes into the function, I can increase this value to get a kind of tighter wavelength. The distance between the peaks of these waves is getting shorter and shorter as I increase the value of B, or the frequency of this sine function. The next thing we can do, or the most obvious thing perhaps, let's get our basic function back, is slide it up and down. And this works just like any other translation on a function, where we can move things up and down by adding to whatever the output was of the function. Simply moves it up and down our graph. And finally, the fourth thing we can do to our function is horizontal translation. And hopefully you guys recall some of the things, I'm going to put a plus in here, hopefully some of the things that we've done with quadratics and other functions, that changing the input to the function, adding or subtracting from the input to the function, translates it left and right. You get that kind of horizontal shift when we add inside the function, and that vertical shift when we are adding after the function. And again, we get that same effect where when we're adding, it appears to move to the left, and when we're subtracting from the input, it appears to move to the right. So that kind of reverse notion that we discussed in detail when we were looking at functions. These are the ways that we can translate or modify a trigonometric function. And obviously we still deal with the cosine and the tangent as well, which have similar effects. And here in this sort of stuff folder, I can see that relationship to the circle. If I change my amplitude, I'm essentially changing the radius of the circle that I'm rotating around, which affects how high up and how far down my y value goes as I rotate around. Similarly, if I increase the frequency of the function, it's essentially like changing how fast I'm jumping around the circle. So as I rotated just a maybe about 45 degrees or pi over 4 radians, I've gone through more of the circle than I normally would have. I'm sort of amplifying or speeding up the outputs of the function. This is a little bit more difficult to visualize with the circle, but it's like moving faster around the circle, and we'll discuss that in more detail as well. And finally, left and right, it's kind of like shifting the circle along, so the function is following it. And horizontal and vertical translation, you can kind of see they're a little bit more obvious to visualize. So those relationships to the function and how we modify it will be really key, and this will be your introduction to sort of visualizing those relationships and how we transform trigonometric functions. I'm going to send you these links so you can play around with it and have lots of fun with trig functions.